Okay, welcome to another lab. In this lab, we're going to be talking about trajectories and how objects move when they're flying through space. This is fairly classic physics, and the way it works is that there are essentially two kinds of movement going on at once. In the horizontal direction, we have constant velocity motion. So the velocity stays the same, and there is no acceleration horizontally, and that means that the x position at any time is equal to whatever the velocity is in the x direction times that time. The velocity stays constant. There's no reason for there to be a velocity of time equation because it always stays the same. Vertically, something else happens. Vertically, we have constant acceleration motion. And constant acceleration motion means the velocity changes all the time. The velocity differs as time goes by. In fact, we have an equation for the velocity at any time, and that's equal to the velocity at t equals 0 plus the acceleration times t. And because while the thing is accelerating, it's also moving, we have a formula for the y position at different times t. That's given by whatever y is when you start the process plus the initial y velocity times time plus 1/2 a t squared. So the y position changes as time goes by. The y velocity changes. X, on the other hand, has constant velocity. Its velocity is always the same, and it just rolls along at a constant speed. Now, the lab we want you to do is to explore this kind of thing. What we want you to do explicitly is to find yourself a nice bright light, like a street light or something that shines like so, and then we want you to stand under the light and take a ball or something and try tossing it in an arc from you to your assistant. And while it's going by, I want you to watch the shadow of the ball on the ground. And what you should see is this shadow, which is the projected horizontal position of the ball. This moves at a constant velocity. Doesn't speed up, doesn't slow down. It's always moving the same distance in the same amount of time. The up and down motion is not. That starts out at one velocity, slows, eventually stops moving up and down, and then starts falling down again. But the horizontal motion is pure constant velocity motion. That's what this lab is all about. Okay, what we're going to do is continue working with trajectories. And in particular, what I want you to do is to take the Nerf gun you used last week, and we're going to have you shoot it outside and measure the maximum height and the maximum range of your Nerf gun and compare that to what you calculate for those numbers using the muzzle velocity we got last week. So let's go over some trajectories again. How do trajectories work? Well, the trajectory, what happens is that you throw something and it goes through a nice big arc, like so. And What goes on physically with this is that horizontally, we have constant velocity motion, and vertically, we have constant acceleration motion. And these two work together to make a nice big arc trajectory. What I want you to do today is to use the numbers you measured last week, calculate what you should get for the maximum range and the maximum height, and then I want you to go outside and actually see what you can find with the same Nerf gun you used last week. Nerf darts are not ideal for this because they're built to have a lot of friction, but you should get something sort of on the same order as what you calculate. So let's go through how to do this calculation before you go out and try to do this. Now, first off, let's find for the maximum height. To understand how to calculate the maximum height, it's nice to stop and think about this for a little bit. What happens? And what happens is you shoot it straight up, and it goes up for ways, and then it stops, and then it comes down. It's reached its maximum height when its vertical motion has all run out, and it's come down to zero. So what that means is the y velocity at the peak height, so let's call big T the time when it hits the peak height, which is the initial velocity minus the acceleration, which is g, times the time it goes by. That, at the moment of its peak height, this velocity has come down to zero. In other words, we can just invert this to get the amount of time that takes, and we'll bring this to this side and divide by g, and we get the time that takes equals v0 over g. Now, using the numbers I got last week, I had v0 equals 15, g is 9.8. This is roughly a second and a half. That's the amount of time it takes to get to its maximum height. How high does it go in that amount of time? Well, to do that, we have to use the other equation and say y at big T equals vy0 times big T plus 1/2 at squared. Plug in numbers for this. This is the 15 meters per second we got last week. This is a second and a half. This is minus 9.8, and that's 1.5 squared. So I get 15 times 1.5 minus 1/2 times 9.8 times 1.5 squared. So I get 11.25 meters, which is a perfectly reasonable height for a Nerf gun to go. So that's roughly correct. To get the maximum range, it's easiest to do this if you think about, well, the time for the whole arc is twice the time it takes to get to the top, and the horizontal distance it goes over the whole time will be twice as far as it goes when it gets to the top. So if we can figure out how much time it takes to get to the top, then we can figure out how much time it takes to go the whole distance. And that is fairly easy to get. Let's call big T the time to the top and figure out how long does that take. Well, at the top, the vertical velocity has gone down to zero again. So we get 0 equals vy0 minus g times big T. And when it's moving in a horizontal arc, its initial velocity is not the same as it was over there, because you start off at an angle, so its vertical velocity is just the muzzle velocity times the sine of the angle minus GT. The angle to fire it at is 45 degrees. The sine of that angle is 0.707. So we get 15 again times 0.707 minus 9.8 times t, and t equals 15 times 0.707 over 9.8, or this is about 1.05 seconds. So it reaches its peak about a second after it takes off. How far does it go horizontally in that time? Well, x at big T is just horizontal motion. It's Vx0 times big T. Vx0 is V0 times cos theta times big T. Plugging all those numbers in, we get 15 times 0.707 times 1.05. And that's 11.25 meters. That's half the total range. So the real range, the complete range, is 22.5 meters. That's again a reasonable number for a Nerf gun. Friction plays total havoc with Nerf guns. So you should think of these numbers as kind of upper limits. How to do this experiment, I really leave up to you. How do you measure the height? Well, it's easy if you shoot it off next to a building and count stories. That's the best way to do that. The range, you just need a big parking lot to fire it off and see how far it went. Good luck with this. This is kind of a fun one. And send me the numbers you get.